Okay, guys, welcome back. I'm going to go back to the Project Euler problem number 3, which I kind of skipped over to head out and figure out how to find prime numbers. Because we do need to figure out, well, one of the ways you can do this is finding a prime number. We won't actually be introducing that here. We'll be doing something a little bit different. It's going to follow more closely the solution that you'll see when you submit an answer there, um, and it's pretty interesting how this stuff actually works out. So let's go ahead and take a look. Now the prompt for it is the following. Um, the prime factors of 13,195 are 5, 7, 13, and 29. What is the largest prime factor of this number? And it's something like, I think 600 trillion, right? 600 billion and some change. So we're going to be going over how to do that. Fortunately, we're in JavaScript, which means that we don't need to worry about putting this in any sort of special number. For those languages that require or that whose, I guess, usual integer values go up to 2 to the power of 32-ish or whatever. I think you run into issues here, but with JavaScript, we don't run into that issue. So that is kind of nice. I think JavaScript is somewhere around like 2 to the 51st or something like that, 53rd. So let's get started. Largest prime factor. Um, when we find a prime number, um, say, in the case of 100, uh, we're going to first check to see if it's divisible by 2. And if it is, we're going to divide by 2. And then we're going to check to see if it is again, because now we're saying that this number that we're checking is actually half of what it is. So we'll check it again. So we're checking to see if 50 is divisible by 2, and it is. So we're going to do it 25. While we're doing that, we're going to set the last factor number to 2, because we've said that it's divisible by 2. We don't care that it's divisible by 2 twice, because divisible by 2 twice just means it's divisible by 4. 4 isn't prime. Doesn't matter. So that's what's going on here, because 2 is a special case of primality, being the only even prime number that there is. So we put it over in a special case here so that we can iterate our factors by odd numbers. You can see the factors start out at 3, and we're iterating by the odd numbers by adding 2. Because when you add 2 to an odd number, you're going to get an odd number. In fact, if you start at the first odd number, you will get every odd number in sequence. So setting max factor to math dot square root of the number that we're passing in. Yeah, I mean this part's, I've gone over this in some of the other videos, that you only need to check up to numbers that are the square root. It's a little bit more complex here. There can only be one number greater, which is prime, greater than this. For any number, there is only one divisor, at most one divisor, which is prime and greater than the square root of that number. So on the surface, it looks like we might be stepping into some dangerous territory, because we're only checking up to the numbers that are divisible, and we could run into an issue like 51. 17 is the greatest factor there, and 17 is definitely bigger than the the square root of that. But I believe if we run this, should get the correct answer. Yeah, so we're going to go into why that's the case. So this part's straightforward enough. That makes enough sense. This part is the part where it gets tricky. So let's dig in. So we've got a while loop here. We could use a for loop. There's a lot of different conditions, and there's a lot of different ways that we're iterating. So um, we've got two different conditions, and we've got two different iteration steps. The obvious iteration step is right here, but because this is part of the condition, um, max factor is part of the condition, we're changing it right here in the if statement. That's also something that's going on. So it's, you can still do it. You iterate, factor equals factor plus 2 up here, and you could still get by. But we've also got to, we would have to declare these either in the for loop or outside of them anyway. I've left them outside. It's up to you. Actually, yeah, we could declare them both outside. Last factor needs to be outside for sure. These two can be inside. So we've got this while loop. Upper bound, number that we've passed in, divisible by 2 for as many times as it can be. As long as that's greater than 0, we'll go through this. Also, in addition to that, this number factor has to be less than or equal to this number. So if both of those hold, first thing we're checking for is if this number is divisible by this number. And if it is, then we are going to set that number, this number, to itself divided by that factor. And we're going to set this variable last factor equal to this current number. Then, just to make sure, just to check to see if it's divisible by that number again, we're going to enter a while loop, just dividing out any other times. Basically what we're doing up here. So in cases like 27, right, we're just going through and making sure we're dividing all the instances of 3 out. 27 maybe isn't the best example because it's only divisible by 3 in itself and 1, obviously. Better cases if you multiply that by 4 or something like that, or 8. So 4 would be 108, right? You're just going through and dividing out all the times that it's divisible by 3, or 5, or 7. Second thing, we're going to set the new max factor to this upper bound that we've just redefined in both of these steps. So math equals, or max factor, same thing up here, but upper bound's changed, so we need to reset this value. That's why we're only doing it in the if clause, because it's only going to happen in the if clause that we need to reset it. Then we iterate factor plus 2. Now, you're looking at this and thinking, wait, we're checking all odd numbers here, so if it's something's divisible by 9, there's a possibility that we're going to be dividing something by 9. Well, no, actually, we're not, because that's why we've got this while loop here. So first thing it's going to do is check for all instances where it's divisible by 3. Now, as it turns out, if something's divisible by 9, or divisible by 9, then it's divisible by 3 twice. But if we divide 3 out of it, then by the time we get around to 9, that number won't be divisible by 9. So to take an example, concrete example, something like 72 is divisible by 9, right? If you divide 72 by 9, you're going to get 8. But in this sequence, what we're doing is first we're dividing it by 3, and that gives us 24. 24. That's no longer divisible by 9 now. It's still divisible by 3, actually, though, because it is. And that's going to give you 8. And then, it wouldn't have gotten to that point anyway, obviously, because we would have been checking the 2's, but presuming we didn't. So that's why we can check odd numbers that aren't prime, because they will never pass this clause. This is only going to yield true if the number is prime. Now, it won't always register true if the number is prime, but it can only register true when the number is prime. So 5 could pass, but 25 will never. 5 need not pass, however, in cases like 72. It's not going to pass for 5 here. It's not going to pass for 25 either, though. So that's why we can do something like that. The if is always going to be false in cases where the factor is not prime, because if it's not prime, it's going to be divisible by that number is going to be divisible by something that we've already rooted out of the upper bound, 2, or a previous odd number, because all prime numbers are divisible by all composite numbers are divisible by prime numbers that are less than itself. So that's why we can do something like this. So we go through that whole instance. Once we're done, we check to see if the upper bound is 1. If it is, then we're going to return this number. And if it's not, if it's equal to 1, not divisible by 1. If it is equal to 1, what does that tell us? Well, it tells us that we rooted out all of the numbers possible, and we can safely return the last number. If we haven't rooted out all the numbers, then that means there's still a number that the original upper bound is divisible by, and that is the current value of upper bound. So in this case, we'll watch how that works. You can see the answer is 6,857. Watch what happens if we do something like last factor. Let's run it again. We got a different answer. So what does that tell us? That tells us that, in fact, this is not true. That upper bound is not equal to 1, and that's why we're passing an upper bound. In fact, in this case, upper bound is that instance where the number that we're passing in has a prime number, or has a divisor, which is prime, greater than its own square root. And that's how we find it, by checking to see if this number is equal to 1. And if it's not, that tells us that the number, that all this instances of us dividing has yielded the prime number that is the divisor for it. That's greater than the square root. Numbers don't always need that, though. And in the cases where they don't have a value that's prime greater than its own square root as a divisor, upper bound is going to equal 1. And that's, so, when we passed in 51, that's another instance where see what happens. I don't think this will even work. I think it's going to return 1 here. It's going to return 3. Oh, because 17 is divisible by, or 51 is divisible by 3. So hopefully that smaller scale example is illuminating as to what's going on here. When we check a number like 51, we could ignore this. We're going to start out here. And the first thing we're going to do, since the max factor is going to, what is the max factor going to be? It's somewhere in between 6 and 5. So this is going to be true. The upper bound is still going to be greater than 0. Upper bound is going to be divisible by the factor. 51 is divisible by 3. So we're going to say upper bound is equal to itself divided by 3. The last factor equals 3. It's not going to go through this again because it's only divisible by once, but we're now going to reset math factor, or max factor, as equal to math.square root upper bound. Upper bound is now equal to 17, so we're going to check for 17. The square root of 17, slightly above 4. and we're going to iterate. Factor is now 5. So this is still true, but factor is now equal to 5, and max factor is now equal to 4 and some change. So this is no longer true. So the while loop is done. So now upper bound does not equal 1. Upper bound equals 17. So that's false. So let's pass in upper bound. And that's why we get 17. It's a little bit more complicated than the other ones that we've done. This is far less intuitive, but it's probably the most efficient way I think that you could do something like this. Excluding maybe cleaning up some of the declarations and stuff like that. But we don't need to store an array of prime values this way. We're just dividing numbers out of the number that were initially given. But yeah, I hope you guys enjoyed the video. Obviously, please subscribe, smash the like button, etc., etc. And yeah, I'm just going to keep on going through Project Euler, whatever else, whatever other algorithms I think are interesting. Bye.